Hello, humans, and welcome back to my science studio. So, today I want to start by showing you something really cool. Let's look at two elements that could not be more different from each other: sodium and chlorine. Recall in a previous lesson that sodium is a metal. It's a solid, it has luster, meaning it's shiny, and it has all the other typical physical properties of metals. So, it's ductile, malleable. But chlorine, on the other hand, is a nonmetal. It's actually a yellowish gas and it has all the properties that nonmetals usually have. But here's the crazy part: chlorine gas is toxic, and it was actually used in warfare and sprayed across enemy lines during battle because of how dangerous it is. So here's the question I always ask my students: how can two substances that are so different, and in chlorine's case, so deadly, come together to form something we literally eat every single day? And that's sodium chloride, better known as table salt. And the answer leads us into today's topic: how atoms get together, and how forming chemical bonds makes substances with completely new chemical properties. But before I jump into ionic versus covalent bonds, I want to talk about a really important periodic trend called electronegativity. Now, in a separate video, I'll explain all the periodic trends from ionization energy, electron affinity, atomic radius, so stay tuned for that one. But for today, just remember this: electronegativity is an atom's ability to pull an electron pair closer to itself during a chemical bond. And there's a trend. As you move across a period, so from left to right, electronegativity increases. And as you move up a group, so bottom to top, electronegativity also increases. So if I draw an arrow from the bottom left of the periodic table up to the top right, electronegativity is increasing along that arrow. And here's how I always picture it: a game of tug of war. Two teams are pulling on a rope. The stronger team is more electronegative, meaning they pull the shared electrons closer to themselves. Fluorine, by the way, is the champion of tug of war. It has the highest electronegativity value on the Pauling scale. And just a quick note, these numbers that you see here are not printed on the periodic table. They come from the Pauling scale, which is something that your teacher will most likely give you. Now, teachers also love to test this next part. To figure out whether a bond is ionic, polar covalent, or nonpolar covalent, you can look at the difference in electronegativity. That's what the little triangle symbol means. It represents the difference between two electronegativity values. And we'll calculate a few in a minute. But a quick reminder: remember that the noble gases are like royalty. They're stable. They're in group 8A of the periodic table. They're the cool kids, right? They're chilling. They already have a full octet or a full valence shell. So they don't really bond and they don't pull electrons towards themselves. And that's a big reason why fluorine, not neon or helium, has the highest electronegativity. Now let's talk about the first type of bond: ionic bonds. And you know what? You can hear it in the word ion. An ion is an atom with a charge, positive or negative. In an ionic bond, you have a metal and a nonmetal, and the metal is always written first. You see, sometimes students flip the order, but nope. Metal first, nonmetal second. Ionic bonding involves the transfer of valence electrons, meaning one atom donates and the other accepts. As a rule of thumb, remember, metals tend to donate and form cations, or positive ions, and nonmetals, they tend to accept and form anions, or negative ions. Let's walk through the classic example that we started this lesson with: sodium chloride. Sodium, or Na, is in group 1A. That means it has one valence electron. Now recall that atoms form bonds because they want to achieve a stable octet, meaning 8 electrons in their valence shell. So ask yourself, is sodium going to gain 7 electrons or donate 1? It's going to donate, exactly. Chlorine, meanwhile, is in group 7A. You see, it already has 7 valence electrons and only needs one more. So when sodium donates its one electron, chlorine happily accepts it. And now both of them achieve a full octet. And when this happens, sodium becomes Na plus and chlorine becomes Cl negative. And remember, opposite charges attract, and that attraction forms the ionic bond. Now, later on in this series, we'll dive into reactions, but here's a quick taste. When NaCl dissolves in water, it undergoes an ionization reaction, meaning the salt separates into Na plus and Cl negative ions. Water molecules surround those ions and stabilize them. But I won't get too deep into that today. If you're interested to know more on how this works, please drop a comment below. Now, if your teacher wants you to calculate the electronegativity difference, this is how you do it. On the Pauling scale, sodium has an electronegativity of 0.9, while chlorine is 3.0. So if you subtract 3.0 minus 0.9, you get an electronegativity difference of 2.1, which is greater than 1.8. So the bond is considered ionic. Now, let's talk about the second type of bond, covalent bonds, which happens between two nonmetals. In covalent bonds, there's no transferring, meaning no one's giving or taking anything. Instead, the atoms share valence electrons. But is all sharing equal? No. So back to tug of war. We have two teams that are sharing the rope, but one might be pulling harder and will evidently win, right? So let's look at H2O. I'll draw the Lewis structure here. And as a side note, I will create a Lewis structure video in the next coming weeks. But until then, normally you'd put the least electronegative atom in the center, but you never put hydrogen in the middle. So oxygen will go in the middle, and the hydrogen's on the outside. Oxygen is in group 6A of the periodic table, so it has 6 valence electrons, and hydrogen is in group 1A, so it has 1. If you connect the dots, that forms a single bond, and you get water. Now let's ask the important question. Who's more electronegative, oxygen or hydrogen? Well, without looking at the Pauling scale, oxygen is all the way to the right. It's in group 6. And if you compare that with hydrogen, which is in group 1, oxygen is more electronegative. And in fact, according to the Pauling scale, its value is 3.5 compared to hydrogen that's 2.1. So it is more electronegative than hydrogen. So when they share electrons, the oxygen pulls harder, and that creates an unequal sharing. And you may have seen this symbol before, this delta minus for oxygen and this delta plus for hydrogen. It's not that oxygen is gaining electrons, it just has more pull. So the same tug of war idea, both teams hold the rope, but oxygen is the stronger team pulling it towards its side. So if you calculate the electronegativity difference, in other words, you take 3.5, which is the value of oxygen, minus 2.1, which is for hydrogen, you'd calculate the difference to be 1.4. And that falls between 0.5 and 1.8, which is what we consider a polar covalent bond. Now, most teachers won't make you calculate this every time. And for the most part, if you know the trend, you know oxygen will always be more electronegative than hydrogen, which makes water a polar molecule. But what about an equal sharing? That's where you get nonpolar covalent bonds. You see, if both teams in tug of war are equally strong, neither side wins. The rope stays centered. They share equally. And a perfect example are the 7 diatomic molecules. Remember the mnemonic? Have no fear of ice cold beverages? So take the example of oxygen gas. Oxygen is bonded to itself. So the electronegativity values are going to be the same. So if you take 3.5, which is the electronegativity value for oxygen, and subtract it by 3.5, It's going to be 0. So there's a total equal sharing of valence electrons happening here. And as you can see, nonpolar covalent bonds have an electronegativity difference that falls between 0 and 0.4. All right, before we wrap up, I'm going to give you 5 quick examples. If you want to try them on your own first, go ahead and pause this video. Give them a shot and then resume once you're ready. Let's try NgCl2. Magnesium is a metal and chlorine is a nonmetal. So when you have a metal plus a nonmetal bonded together, that's your clue that this is an ionic bond. And recall that ionic bonds involve a transferring of valence electrons. So metals like magnesium are more likely to donate their valence electrons to nonmetals like chlorine, which will happily accept those electrons. Now, what about chlorine gas, or Cl2? Recall that this is one of the 7 diatomic elements. And because it's 2 nonmetals bonded together, it's covalent. But now ask yourself, is there an equal or unequal sharing of valence electrons? In other words, is the bond nonpolar or polar? Well, because it's the same atom bonded to itself, if you subtract the electronegativity values of the 2 chlorines, you'll get 0. And anything close to 0, so about 0 to 0.4, is considered nonpolar covalent. Now, what about LiBr? Well, lithium is a metal and bromine is a nonmetal. So again, if you have a metal plus a nonmetal, you get an ionic bond. Now let's look at HCl. Hydrogen and chlorine are both nonmetals, so this is definitely a covalent bond. But you see, chlorine is way over on the right side of the periodic table in group 7A, and hydrogen is up to the left in group 1A. So chlorine has a much higher electronegativity, so it's going to pull harder on those shared electrons, which makes the bond an unequal sharing, which means that HCl is polar covalent. Thank you guys so much for watching. If you found this lesson helpful, please like and subscribe to my channel. In the next episode, we're going to dive into nomenclature, so how to name compounds, but the easy way. So stay tuned, and as always, please come back to my science studio for more chemistry made simple lessons. See you guys next time.